Eighth grade, we are in week 16 talking about electromagnetic waves. Today you should be able to explain radio waves. William can't help rocking out when his favorite song starts playing on the radio. Do you like to listen to the radio? Did you ever wonder how music travels from a radio station to a radio receiver? How do the sounds travel through air and buildings and everything else in between you and the station? Well, the answer is electromagnetic waves. The electromagnetic waves consist of vibrating electrical and magnetic fields. They transfer energy across space as well as through matter. Electromagnetic waves vary in their wavelengths and frequencies, and higher frequency waves have more energy. The full range of wavelengths and of electromagnetic waves is called the electromagnetic spectrum. It is outlined here. Electromagnetic waves on the left side of this picture are called radio waves. Radio waves are electromagnetic waves with the longest wavelengths. They may have wavelengths longer than a soccer field. They are also the electromagnetic waves with the lowest frequencies. With their low frequencies, they have the least energy of all electromagnetic waves. Nonetheless, radio waves are very useful. They are used for radio and, believe it or not, television broadcasts and many other purposes. So here's a question for you. Based on this picture, what is the range of frequencies of radio waves? Take a second and think about that for a second. Okay, so the range of frequencies of radio waves is between 105 and 1012 hertz, or waves per second. Let's talk a little more about radio waves. In radio broadcasts, sounds are encoded in radio waves, and then the waves are sent out through the atmosphere from a radio tower. A radio receiver, or radio, detects the waves and changes them back into sounds. You may have listened to both AM and FM radio stations. How sounds are encoded in radio waves differs between AM and FM broadcasts. AM stands for amplitude modulation. Amplitude modulation. In AM broadcasts, sound signals are encoded by changing the amplitude or maximum height of radio waves. AM broadcasts are longer wavelength radio waves than FM broadcasts. Because of their longer wavelengths, AM waves reflect off the layers of the upper atmosphere called the ionosphere. You can see how this happens in a picture that's coming up. Because the waves are reflected, they can reach radio receivers that are very far away from the radio tower. Meanwhile, FM stands for frequency modulation. In FM broadcasts, sound signals are encoded by changing the frequency of radio waves. Frequency modulation allows FM waves to encode more information than does amplitude modulation. So FM broadcasts usually produce clearer sounds than AM broadcasts. However, the relatively short wavelengths of FM waves means that they don't reflect off the ionosphere as AM waves do. Instead, FM waves pass through the ionosphere and out into space. This is also shown in the picture coming up. So here we have examples of AM and FM on the left-hand side. On the top is AM. A carrier wave is generated by the transmitter. The sound signal is picked up by the microphone, and the electrical image of sound formed by the microphone is fed into the amplitude modulator. The amplitude modulated carrier wave is then transmitted. The AM radio signal that is transmitted has a modulated amplitude. Notice that the heights of the wave are different in different places. The FM wave, again, starts with a carrier wave generated at the transmitter. The sound signal to the microphone is turned into electrical signals, and in this case, they modulate the frequency. The frequency modulated carrier wave, the FM radio signal that is transmitted, is slightly different in frequency as we go from wave to wave. Notice that the FM waves actually have enough energy that they're able to escape the ionosphere and travel out into space. AM waves, on the other hand, have less energy and bounce off the ionosphere and back to the Earth's surface. The composition of the ionosphere changes somewhat from day to night. The changes make the nighttime ionosphere even better at reflecting AM radio waves. How do you think this might affect the distance AM radio waves travel at night? Pause the video for a moment and think about this question. Write down your answer. Back already, huh? All right. So how does the changes in the ionosphere affect radio waves? Well, with greater reflection off the ionosphere, AM waves can travel even farther at night than they can during the day. Radio receivers can often pick up radio broadcasts at night from cities that are hundreds of miles away. So, as we look at this chart, we also see television. Television broadcasts also use radio waves, which was very surprising to find out. For TV broadcasts, sounds are encoded with frequency modulation, or FM radio waves, and pictures are encoded with amplitude modulation, or AM radio waves. The encoded waves are broadcast from a TV tower. When the waves are received by television sets, they are decoded and changed back into sounds and pictures. So, in summary, electromagnetic waves vary in their wavelengths, frequencies, and energy levels. The full range of electromagnetic waves make up the electromagnetic spectrum. Radio waves are electromagnetic waves with the longest wavelengths, lowest frequencies, and least amount of energy. They are used for radio and television broadcasts and many other purposes. In radio broadcasts, sounds are encoded in radio waves by changing either the amplitude, AM, or the frequency, FM, of the waves. The coded waves are broadcast from a tower and changed back into sounds by radio receivers. In television broadcasts, sounds and pictures are encoded in radio waves, broadcast from a tower, and changed back into sounds and pictures by television sets. Well, if you're able to explain radio waves at this point, go on to the questions. But if not, feel free to view that video again. And remember to take some notes. We'll talk to you later. Bye now.